In this section, we will discuss case history number 3, a field-wide liquid-liquid application. This third example is about the use of many optical monitoring systems in a field-wide application in the North Sea region. As usual, all the details, the results, conclusions, and the challenges on this case history can be found in the public domain in an SPE paper co-authored with the operator. Now let's start with introducing the field. This is the Buzzard field located in the North Sea region and 60 kilometers from Aberdeen. It was discovered in 2001. The first set of wells were completed in 2006. Oil production started in 2007. The optical monitoring system was part of the completion plan from the very early stages. And this is very important because if you remember the discussion we had in an earlier section when we compared the flow measurement systems, surface measurement system versus the downhole measurement system, we stated that it was very important to engage with the operator at an early stage so that the downhole monitoring equipment could be part of the completion process. And this was the case for the optical monitoring system in this application. The Buzzard field production is above 200,000 barrels per day, and the injection rates could reach very high values when needed. So let's talk about the monitoring approach and the field expansion capability. The monitoring approach is very efficient because the topside instrumentation, which consists of a number of modules bounded by this red box, drives all the optical monitoring systems in all the wells in the same field. So the design is such that as new wells are added to the field, the optical monitoring system in that new well is connected to the topside instrumentation. The optical monitoring system for each well consists of an optical flow meter, an optical PT gauge, and a DTS system. And all these monitoring systems in all the wells are connected to the topside instrumentation. The topside instrumentation consists of a number of modules. The reservoir monitoring system is the controller. There is an electro-optical module for the optical flow meters. So all the optical flow meters are connected to this EOM through an optical switch. Likewise, there is a BGI, the Bragg grating interrogator for the optical PT gauges. And there is a DTS box for the distributed temperature sensing systems. So let's demonstrate how the expansion process works. Let's assume that the operator has a number of wells in the field, well A, well B, well C, and so on. And they would like to add a new well, let's call it well N, to the field. So what needs to be done is to connect the optical flow meter, PT gauge, and the DTS system to their respective boxes in the instrumentation, the flow EOM, BGI, and the DTS box through optical switches. And that completes the expansion process from a reservoir monitoring perspective. This represents a significant advantage compared to other potential solutions which might require individual topside data acquisition systems. In this case, there is only one topside instrumentation. This is a rack system, and any addition of monitoring system means that it's going to be included to this topside instrumentation. So this also means significant cost savings for the operator because there is no secondary topside instrumentation. So there is one point that I would like to make on the optical PT gauges. As you see from this schematic, the PT gauges are on separate single mode fibers, and this was by choice. The operator decided to put the PT gauges on a separate fiber to increase the reliability of the system. It was possible to use the optical flow meter and two PT gauges to put them on one single mode fiber due to the fact that the optical meter and the PT gauges use different wavelengths for their respective signals. So let's talk about the data frequency. Currently, there are 43 wells in the buzzard field. Now, the optical flow meter measures the flow rates, and it outputs the flow rates, standard flow rates, and the inline flow rates every 90 seconds. So with one flow meter, the time interval between two consecutive data points is 90 seconds. However, we have many flow meters in the field, and there is one topside instrumentation. So the processing power is shared by the number of optical flow meters. So that means that the time interval between two consecutive data points increases proportionally by the number of flow meters. In this case, with n being 43, that time interval corresponds approximately to 1 hour. Now, there is some pending feature projects that would decrease this 90-second data acquisition time for one flow meter. That would go down to about 30 seconds. For the PT gauges, the data acquisition is very fast. It is 1 second time interval, and having multiple wells is not significant. It is the same time interval because the BGI is a very fast system. For the DTS, it is similar to the flow meter. The data acquisition time for one DTS trace is about 60 seconds, and that number increases proportionally with the number of wells. So in this case, for the buzzard field, for 43 wells, the time interval between two consecutive DTS traces for one well corresponds to 43 minutes. And this data frequency has been sufficient for the operator. In our discussions with the operator, they stated that that is basically sufficient for them, this data frequency. However, if they want to increase the data frequency anytime, it is possible to add another topside instrumentation, a secondary instrumentation, so that the data acquisition from these wells can be shared. So this case history demonstrates the flexibility and expandability of the optical monitoring systems. And because there is only one topside instrumentation, it also highlights the significant cost savings for the operator in a field-wide application.